Okay, quadratic equations and inequalities, the review. So quadratic functions lead off with y equals ax squared plus bx plus c, or f of x. And our first method of solving is to graph the function and to find the x-intercepts, or the zeros. It's the x-intercept of the graph or the zeros of the function. So that's a graphical solution. You could do that by setting y1 equal to the quadratic. y1 is our quadratic function, and we could set y2 equal to 0, and then we find the intersection point. And what we're interested in is the x-coordinates of the point of intersection, since we know the y values are 0. Or just graph y1 equals the quadratic function and then find the zeros of the function. So that's solving graphically. Usually involves rounding, nearest tenth, nearest hundredth. I'm not going into great detail on that. And then we get quadratic equations. So ax squared plus bx plus c equals 0. So when you're going to, first of all, we have an equation, right? It's equal to something. It's not a function where it's y equals or f of x equals, which is the entire curve. It's an equation, and this has to be equal to 0. And your first step really in solving any of these is to make sure that you rewrite it so the equation is equal to 0. I'm not going to go into the different methods of factoring. Just simply state that factoring is a method of solving, and so let's do one by factoring. Okay, so the first step is to rearrange. This has to be set equal to 0, so we will get 2x squared minus 5x, subtract 1 from both sides, minus 2 is equal to 0. And now we factor this. Okay, what method you use to factor, totally up to you. The important thing, though, is to check. I need two numbers that are going to multiply to negative 2 and give me a negative 5 here. So if I put a negative 2 here, oh, sorry, wait, this is plus 2. Right, we're going to subtract 1 from both sides. I was kind of wondering why this wouldn't factor. So this will be a minus 2 and a minus 1. Now, anytime you factor, take a quick moment. 2x squared minus 4x minus 1x is minus 5x plus 2, and that's equal to 0. The zero product property says that either this factor, 2x minus 1, is equal to 0, or the other factor, x minus 2, is equal to 0. So we can solve these. 2x minus 1 equals 0. 2x is 1, x is 1/2, or x minus 2 is equal to 0, which means that x is equal to 2. Similarly, or along those lines, sometimes we give you the roots. We say, hey, x is 1/2 and x is 2, and ask you to give us a function. So give us the quadratic function that has these roots, or give us a quadratic function, in which case you want to take the root and turn it back into the factor. So you'll be going back this way. Take x equals 2, subtract 2 from both sides, turn it into a factor, making equal to 0. And x equals 1/2, multiply both sides by 2, you get 2x equals 1. Subtract the 1 and turn it into this factor, and then you can FOIL these out and come back to this. Now, we would never get back to this expression, right? That's something we have to start with, but we can get back to the original quadratic. Okay, so given the roots, you need to also be able to work your way back to a quadratic equation, right? Where equation, again, where it's equal to 0. Also remember, look for the key ideas, right? The key ideas for graphing are on page 214, just before the questions, and the key ideas for factoring are on page 229, just above the questions. So for every section that we've done questions on, take a look at the key ideas. The next method of solving is solving by completing the square. The questions are on page 240, and that's where the key ideas are as well. So just give me a moment to clear things up, and we'll look at completing the square. Okay, here's one out of the book. Let's solve this by completing the square. So my first step, since this is equal to 0, I don't need to preserve the negative 3, which tells us that this is as a function, it opens down, and it's vertically stretched by a factor of 3. If this were a function y equals, we would put it into completed square form to find the vertex, and we would need that negative 3 to give us the direction of opening in the vertical stretch. But we're interested in the x-intercepts. We're not interested in what this function looks like or where its vertex is, but only where it intersects the x-axis. So my first step is I can get rid of this negative 3. I'm going to divide everything by negative 3. And I can do that because the right-hand side is 0. Next step, I can move this constant term out of the way, just isolating my x squared term and my x term. I'm going to leave a little space here, and I'm going to move this over 5/3. I'm now going to do our common maneuver in completing the square, which is x minus half of 4/3 will be 2/3 squared. Okay, now, in order to complete the square, I have to take negative 2/3, square it to get 4/9. So I'm going to add 4 over 9. And whatever I do to the left side, I also do to the right side. Now you can contrast that with the method, especially with a negative 3 out front. I would have been adding negative 3 times 4/3, or I would have really been subtracting that, and I would have had to add it on the end. And again, we can't do that with a quadratic function because it would be equal to y, or perhaps a for area, or r for revenue. But in this method of solving, since this is equal to 0, we simply add 4 over 9 to both sides. And 5 over 3 is the same as 15 over 9. So this side is 19 over 9. Now to solve, we use the square root principle, which says take the square root of both sides. Square root of this is x minus 2/3, and that's plus or minus, right? Very important, always plus or minus. Root 19, I'm not going to write this as the root of 19 over 9. Since 9 has a square root, I'm just going to write that as root 19 over 3. And for my final step, I will go 2/3 plus or minus root 19 over 3. Well, my next to last step, I guess. And seeing as they're both over 3, it's 2 plus or minus root 19 all over 3. Now, more commonly, we would see a solution like this coming out of the quadratic formula. And if I was doing this with the quadratic formula, then I would be pretty tempted to change that into a positive and change these into negative, but leave this as a 3. I don't want fractions if I'm doing quadratic formula. So as a matter of fact, you know what? Let's do the quadratic formula on this, as that's really the next step after. So what I'm going to do is just multiply through by negative 1, since I like my a value to be positive. So that makes a 3. B is negative 4, C is negative 5, quadratic formula, which you'll be given, b squared minus 4ac over 2a, but write it down along with the a, b, and c so you can do a proper substitution. Okay, negative b, that's a negative negative 4, which is 4 plus or minus the square root of, this is negative 4 squared minus 4 times 1 times, a is 3, and c is negative 5, all over 2 times 3. And by making the a positive, I don't have to deal with a negative down here. 4 plus or minus the square root. This is always positive, so it's 16. This becomes positive since we're subtracting a negative. And what do we got? 12 times 5 is 60, so it's 16 plus 60, which is 76, over 6. And we have just a little more work to do here. Okay, so 4 goes into 76 19 times, so this will be 2 root 19 over 6. And since all of these are divisible by 2, then I can divide them all by 2. 2 plus or minus root 19 over 3. And you can see that gives us the same answer as we got by completing the square. You can get by using the quadratic formula, and I just made one modification to the original starting equation to turn the a value positive, but didn't divide through by 3, because the last thing I want is to have fractions here. I don't need a fractional b or c value to substitute in. I'd like them just to be integers. So that is also our introduction to solving by using the quadratic formula. So key ideas for completing the square are on page 240, and key ideas for the quadratic formula are on page 253, which also then brings up the discriminant. So let's do the discriminant. Okay, here's the quadratic formula. X is negative b plus or minus the square root of b squared minus 4ac all over 2a. And the discriminant, this part here under the radical sign, if it's positive, then we will have a square root for it, which means I'll have a number that I can add to negative b and subtract from negative b. So if b squared minus 4ac is greater than 0, we will have two real, distinct, that is different, roots. If b squared minus 4ac is equal to 0, then I will be adding and subtracting 0. So my root will just be negative b over 2a. We call that two real but equal roots. And if b squared minus 4ac is less than 0, then we have no real roots, since we cannot take the square root of a negative. And your job, the most important thing is, if b is negative, just remember that b squared will give you a positive value. Okay, so let's do a problem. Let's say that I have 3x squared plus kx plus 5 equals 0. What value or values of k give no real roots? In order to have no real roots, we need the discriminant to be less than 0. It has to be negative. So we'll go k squared minus 4 times 3 times 5 is less than 0. K squared minus 60 is less than 0. K squared must then be less than 60. So we need k squared to be less than 60, so k must be less than, well, in a sense actually k has to be in between the positive and the negative square root. So let's just go up here. We'll solve for k squared equals 60, which is k is equal to plus or minus the root of 60. And 4 goes into 60, so this would be plus or minus 2 root 15. Now, that's where it's equal. That would give us two equal real roots. We need k to be less than, we really need it to be in between those numbers, right? As long as, so, on a number line, here's 0, here's 2 root 15, and here's negative 2 root 15. And as long as my k values are in here, then my k squared values will be less than 60. Okay, so let's relate that back here. So for example, 2 root 15 is root 60. What's something bigger? Root 15, let's say, is around 4. So let's say we put a 9 in there. Right, then if I have k squared, if k is 9, k squared will be 81, which is not less than 60. And similarly, if I tried negative 9. So values that are outside of this range. Okay, so my answer is negative 2 root 15 is less than k, which is less than 2 root 15. Okay, and really just keep in mind when we're solving problems with the discriminant, it's going to be 1 of b squared minus 4ac is greater than 0, equal to 0, or less than 0, and you're going to solve that inequality or that equation and come up with a particular value. And maybe your unknown is in the B position, maybe it's in the C position, maybe it's in the A position, right? But this is what you're going to substitute into one of these three inequalities, and you're going to solve that and come up with an answer. And key ideas for the discriminant are on page 253. So last step is quadratic inequalities in one variable. Quadratic inequalities. Let's say we want to solve the inequality. X squared minus 2x minus 3 is less than 0. Here is the graph. This is the graph y equals x squared minus 2x minus 3. So any point on this will satisfy this equation, y equals. And we want to know when this is less than 0. Well, that'll be the area that's below 0 here, right? In other words, you could say when is y less than 0, right? Or when is my graph below 0? So graphically, you can find these key points. This is -1, and this is +3. So we would say from -1, as long as x is between -1 and +3, then y will be less than 0. So that's a graphical solution. Algebraically, what we do is this. We go with x squared minus 2x minus 3. We set it equal to 0. If we can, we factor this. Okay, let's check the factorization. X squared plus 1x minus 3x is minus 2x minus 3, which gives me my roots. X equals 3, or x is equal to -1. And you have three choices now. You can do roots and test cases, you can do sign analysis, or you can do case analysis, and you can review all of those. I'm just going to do roots and test cases. So I split the number line into three parts. -1, 3 are on here, and we've split into three parts. Less than -1, between -1 and 3, and greater than 3. So what I want to do is I want to show this. I've got x is less than -1. So my test point, I'm going to use -2. My evaluate, so substitute, right, we'll get -2 squared minus 2 times -2 minus 3, okay, which is equal to 4 plus 4 minus 3, which is equal to 5. And so is x squared minus 2x minus 3 less than 0? And the answer is no, not in this particular region. What about where x is between -1 and 3? My test point, I'm going to use 0. So that's 0 squared minus 2 times 0 minus 3, which is equal to -3. And is x squared minus 2x minus 3 less than 0? Yes, it is. So in this region is a solution. And the last region is the region where x is greater than 3. Now, because we know at 3 and at -1 it will be equal to 0. So my test point, let's go with 5. 5 squared minus 2 times 5 minus 3. This is 25 minus 10 minus 3. 15 minus 3 is 12. Is that less than 0? No. So my solution is this. That -1 is less than x is less than 3. And if your original inequality is strictly less than, then you will have strictly less thans or greater thans. If your original inequality includes an equal to, then in your inequalities here you will include equal to's, right? Since it's at this point and this point that things are equal to 0. And so that's solving quadratic inequalities. The key ideas are on page 484. So you can take a look, and if you have to do it algebraically, you may use any one of the three methods, roots and test cases, case analysis, or sign analysis. And that concludes our review of the first 2 units. I won't do any review of the systems of equations and absolute value functions and equations for the CUME. We'll have a quiz on that on Tuesday, and we'll continue from there.